Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the previous classes, we have learned about the organoboron chemistry, and also I think before that we also learned about the some of the organozinc and organocopper chemistry. In today's class, I think I am going to focus on the p block elements, and especially I am going to start with the silicon, and then I am going to move to the sulfur and then phosphorus. So in this course, I am going to talk about the silicon and its physical properties and use, and I am going to introduce you to the organosilicon compound. What are the different type of properties of organosilicon compound, different reactivities. Okay, there will be some name reaction using organosilicon compounds. I am going to highlight them and also try to solve some of the problems. So let us start with the p block elements chemistry. So I am going to start with the organosilicon. I already finished organoboron chemistry. So, I am going to start with silicon and then going to move to either sulfur or phosphorus. So, I am going to cover 3 of this. So, this will be 3 different segments. So, first I will finish this silicon, then I go to the sulfur and phosphorus. So, silicon was discovered in 1824 by Professor John Jacob Berzelius, and it was a difficult task because silicon has a tendency with oxygen to form bonds. So, that is why it took some time to discover silicon. Again it is a group 14 period 3 and it is a p block element. So, in this course we are not going to learn about the elemental silicon, but we are going to learn about some of the silicon compounds. So, let us try to see what are the use of silicon in organic chemistry and material science and also in the drug designs. You can see the silicons are very much used in the semiconductor. I think it is very much well known, it was used in semiconductor largely by silicon. And then of course, so that means you are seeing that silicon and then silicon metal alloy, okay, because silicon is hard. So, you have seen in the previous slide. So, it can be also, if you think about silicon oxygen bonds. So, these are silicon oxygen based polymers. So, these are called silicone, and there are several different varieties of this depending on whatever polymer it forms, straight or branch. So, there will be also the silicon can be used as a silicon oil and also as a lubricant. Then silicone, as I was mentioning you, silicone can be used as a polymers, and then of course silicone can be used also derivatization in the drug. So, that can improve the drug potency or change the selectivity. Okay. So, there are been lot of use of the silicon in everyday life, I can say. And also finally, there are a lot of silicon based reagents which were developed in organic synthesis. So, the other things about silicon, that once you try to learn about anything like about the boron, if you remember at the time also I talk about the first thing, that the coordination number, and then I talk about what will be their bondings. So, here also you can see it, I think silicon comes after the you can see the below the carbon you can see silicon. So, there will be some property which will be similar to the carbon. One of the thing is that similar to the carbon which forms a tetrahedral with sp3 hybridized, if silicon also forms a tetrahedral structures, okay, and also we will have a sp3 hybridization. But at the same time silicon, the major difference between carbon and silicon is that in case of silicon it has the vacant d orbital. Because of that, silicon not only can limit to the tetrahedral structure, it can also go to the penta coordinated or it can go to a hexa coordinated structures. Because this is possible because of this vacant 3D orbitals. So, you can see some example here. These are the, if you have a silicon R3 R4 Si R4 type of compounds, you can see these are sp3 tetrahedral structures. But once you can see some, for this particular compound, this pyridine nitrogen can now give electron density to the through d orbital to form this sp3d, and it could be sp3d2 if you have a silicon tetrachloride with 2 pyridine. So, this 2 nitrogen is giving electron density to the corresponding d orbitals. So, you can see it was tetrahedral, then there is a ligand comes to do it, make trigonal bipyramidal, and then finally it will be, once you have a 6 it hexa coordinated, it will be octahedral structures. Okay. So, this is possible with silicon, but not with carbon because of the absence of the d orbital. So, we have learned about the structure. Now about the bonding, whatever bonds silicon forms. So, if you think about the carbon and the silicon, if you try to compare them side by side, one of the important thing about silicon is more electropositive than carbon. Okay, we are going to come back to that in a minute and how that is controlling it. So, now if you think about that the silicon and then hydrogen bonds, like the bond of carbon and hydrogen versus a silicon hydrogen, the silicon hydrogen bond is much weaker than the carbon hydrogen bond. Okay, this is the two comparison happening here. Okay. So, that is why you are going to see that the silane, which is you are going to see this silicon hydrogen bond, this can be used as a reducing agent, but not the the methane. You cannot find methane as a reducing agent, right? Because of this the bond is the bond energy difference. The other important bond energy difference is once you come to a carbon carbon versus a carbon a silicon silicon. So, silicon silicon bond is much weaker than the carbon carbon bond. That is why you are going to see some chemistry with silicon where the silicon silicon bond is getting cleaved. Okay. We are going to discuss some of the chemistry also. The other important is the bond between oxygen and carbon, that is reverse. The silicon oxygen bond is much more stronger than the corresponding carbon oxygen bond. That is why you are seeing that there are silicon oxygen bonds are using in the silicon, that in that polymer you have seen in the previous slides we have discussed, correct. So, because of that bond strength, these can be used as a polymeric material. The other important factor is if you compare the fluorine bond. So, this is a very important thing, silicon fluoride versus carbon fluoride. See the difference in the energy, 485 versus 582. Okay. Almost 100 kilojoule per 100 kilojoule per mole difference between these two. So, silicon fluoride bond, this silicon fluoride bonds is one of the strongest sigma bond. Okay. So, because of that you are going to see a lot of the silicon chemistry was driven by by using some sort of a fluoride F minus source. We are going to discuss them also. Okay. And then the other thing is you can see there are also I think the other things are pretty much similar with this. If you go to the corresponding chloride, you do not see that much difference. Okay. But it is really so, that means like the fluoride has really high affinity to form bonds with silicon. One of the things about this halogen series also, you see every cases in case especially up to the chloride, you will see the difference is really high. One of the things is once the silicon fluoride, so that kind of indicating that there must be some sort of a back bonding happening between this fluoride and the d orbital of the silicon. Because of this back bonding, these bonds are very strong. Okay. The other important thing, as I mentioned, that if you think triethyl silane versus triethyl, so you are talking about these two structure. So, you have ethyl, ethyl and H versus we are talking about silicon with. So, these are the compound with the below the silicon compound, because of the weak bond energy, this can use as a reducing agent, but not the carbon analog, because you can see the one of the important thing is, as I said, once you come to the carbon versus silicon versus hydrogen, what you are seeing here, that the electronegativity is getting decreased from carbon to silicon, and then you can see it is getting increased. So, once you compare the silicon hydrogen bond versus a carbon hydrogen bond, now if you try to write the electronegativity on the top of it, you can see the difference of electronegativity in case of silicon hydrogen will be much higher. And one of the important thing is, because hydrogen is more electronegative than silicon, so that is why the electron density will be on the hydrogen. Okay, that is what I think very similar thing when I was talking about the corresponding borohydride stuff, if you remember. Very similar, because they are also using as a reducing agent. Here also these silanes are using reducing agent, because these kind of have the electron densities on the hydrogen. So, this can now act as a reducing agent, because of the also the bond energy is weak. So, silicon hydrogen bond is weaker bond, okay, which is kind of given here. Okay. So, I think one of the important thing why silicon halogen sigma bond is stronger than carbon halogen bond. I think I try to explain you that the back bonding between this X lone pair to the silicon d orbital. Okay. So, that is why you think there is a partial double bond formation between silicon and the halogen. Okay. That is why you are seeing the bond energies for the silicon fluoride, the bond energy is so high, okay, because of this formation of this partial double bond. Okay. But that is not possible in case of carbon, because carbon is lacking with double bond. So, you do not able to expect some sort of a back donation like that. The other important fact is, if you try to compare the amine analog, like you have a trimethylamine versus if you have a trisilylamine. Okay. What is the difference here? What they are saying that in case of trimethylamine, it is a sp3 hybridized and a pyramidal shape. But when you come to tricylyl amine here, you see it is saying planar 120 degree. What is happening here? Why there is a difference in the geometry? Again, the important stuff is that once you have some sort of a electronegative element which having lone pair, it can give electron density, that lone pair back donation can be happen to the vacant silicon orbital. If that is happening, what you are expecting some sort of a partial, so that means there will be some sort of a partial double bond character because of the electron donation from the lone pair to the silicon d orbital. If that is happening, what is going to happen? That is going to do two important effect. One thing, that is going to change the basicity. That is why you can see this, these are still stronger base. The trimethylamine will be a stronger base compared to the trisilylamine. Okay. Because the nitrogen lone pair is already giving some sort of a electron density to the vacant d orbital. That is why, because of the electron density partial double bond character, they are getting some sort of a planar geometry. Okay. Now, we are going to talk about the important part of silicon is that alpha effect and the beta effect of the silicon. So, here you can see that once you have the carbon with two different trimethylsilicon, then what is happening? If you have this trimethylsilane and then once you have the n-butyl lithium, okay, then it is, so this is this hydrogen here which is acidic, because you have these two silicon group attached with it. If you treat with n-butyl lithium, which is a strong base, it is going to form this corresponding alpha silyl anion. Now, this alpha silyl anion is kind of used for several different transformations. One of the important transformations is the Peterson olefination, which I am going to explain after a few slides. So, now the question comes, why this alpha silyl anion has some sort of a stabilization or effect. We are going to explain that, because this can be react with aldehyde from a 4-member triester, it can able to form the corresponding vinyl silane. Okay. So, now we are going to talk about what is the alpha effect of silicon. So, what we are saying that the silicon try to stabilize a carbon ion alpha to it. So, this is alpha position, and if you have a carbon ion alpha to silicon, it is getting stabilized through this n sigma star. Okay. So, there is a overlap happening between this sigma star orbital and this n orbital and the non-bonding orbital here. So, that because you have this the negative, you have a carbon ion here, correct. So, that electron, so that interaction between this non-bonding orbital and this sigma star orbital, that orbital overlap actually help to stabilize this alpha anion, correct. So, that is what it is called the alpha effect of silicon. Okay. So, you can see that is why we are seeing that you can able to abstract that proton to generate corresponding lithium alpha to the silicon, which I have shown in the previous slide. Okay. And then the other important effect is silicon. So, I talk about silicon alpha effect, that means if you have a SiR3, then we are talking about if you have this position, it try to form, so this hydrogen can be abstracted to form the lithium. So, this is the alpha position. Now, we are talking about if you have this SiR3 and you have this beta carbon here, suppose you have some Cr3 here and I am talking about this is the beta position. So, it is going to stabilize a carbocation at the beta position here. So, silicon can stabilize a carbocation, or it can able to eliminate in a leaving group in the which is present in the beta position. That means, it can stabilize a carbon center radicals also, and also it can stabilize a carbonium ion or a carbocation in the beta position. How this is happening? Because of this orbital interaction here, because there is a sigma bond between this carbon and silicon that is interacting with the sigma star orbital, and that has to be anti-periplanar, as I mentioned. Only if they are in a have a anti-periplanar, then only this donation can be happening to the sigma star. Okay, so because of that, if you have a halogens, or if you have a leaving group in the beta position, then that is this electron donation can weaken this halogen bond, and that can generate this corresponding carbocation here. Okay. And now you can think about the stabilization of this carbocation can be happening from this some sort of a sigma bond hyperconjugation. So, this sigma bond can give electron density to the corresponding, also can be give electron density to the corresponding empty p orbital here through some sort of a hyperconjugation. Okay. So, we have learned about hyperconjugation in case of the carbon and in case of the carbon hydrogen bond, correct? If you remember that the sigma bond electron density was given to stabilize a carbocation. Here that is happening from the carbon silicon bond. Okay. So, now one of the important thing, because of the hyperconjugation, because of the electron donation, this carbon silicon bond is also becoming weak. We are going to come back to a minute that because of that, if you have a nucleophile here which can now take attack on the silicon and cleave this bond to form a double bond. Okay. We are going to explain that in a minute. So, here we are trying to show you some of the example of this beta effect. One of the example is, I think you must have heard about a compound called allyl silane. So, if you have this compound, these are if you try to treat with aldehyde, these are known to react like this is called allylation reaction. It can attack to the aldehyde carbon, okay, form the corresponding alcohol. Okay. So, if you take this aldehyde, of course, you have to use it in Lewis acid to activate the oxygen, to coordinate with the oxygen to activate this corresponding carbon of the carbonyl group, where the allylation can be take place to form the alcohol. But now, if you try to understand the mechanism, what is happening here, this if you have this olefin here, now if you think about the olefin is giving electron density to attack to the carbonyl group here to generate this corresponding carbocation here. Now, this carbocation is actually forming in the beta position. Once you forming this beta carbocation, now this empty orbitals, the carbon silicon sigma bond can give electron density. Okay. And once that is happening, once that electron donation is happening, the your nucleophile in the medium which can able to come and attack on the silicon, cleave the carbon silicon bond to form a double bond here. Okay. The other example also given here. So, you have a reaction of allylation with a nitrine, very similarly you are generating a carbocation here which is the beta position and finally forming the double bond. Okay. We are going to discuss some of this reaction also later on when we talk about the allyl silane chemistry. The other important fact about that we have learned about the SN1 SN2 reaction for carbon, correct? I think we are very familiar with SN1 SN2. But here what we are going to learn here, that if you have a corresponding tertiary carbon compounds with a halogen, correct? So, you have tertiary chloride. Okay. So, now if you have a terbutyl chloride, you try to react for a substitution reaction, you mostly end up going for a SN1, because you can see the SN2 is not possible because it is already a tertiary, and then also if the backside attack is getting hindered. So, it is going to go for SN1 because it will form a stable carbocation and then the nucleophile can attack to form the corresponding product. But now in case of silicon, it is the steric is not a problem here, because silicon because of the presence of this d orbital, the nucleophile can attack silicon to get to this pentavalent intermediate. Now, you can see silicon is coordinating with the 5 different groups here. and now there will be cleavage of this carbon silicon, the silicon chloride bond to form this corresponding product. Because of the silicon having this d orbital, this attack is possible here. Okay, that is why you can see from terbutyl, so if you have a 3-methyl here, instead of terbutyl it is a 3-methyl with silicon and chloride. So, it is a trimethyl silicon chloride can able to participate in the SN2 reaction to get to the corresponding product. I think there will be silicon here instead of the carbon. So, nucleophilic substitution of silicon always a bimolecular pathway. That means you have seen that the substitution is happening, but through a intermediate where you can see it is a pentavalent silicon, you can formation of a minus charge there, and then finally the cleavage of the leaving group and forming the corresponding product. So, now silicon can undergo two different things. It can undergo the backside attack, which you will be seeing very similar to the carbon for inversion, or you can see a retention with a flank attack. It can attack, it can go through a flank attack there, it can, but again in case of the flank attack, it can go for these trigonal bipyramidal structures, okay, and there will be a retention of the product. So, both cases, as I mentioned, it is not like a carbon where you see it will follow like a SN1, depending on the steric, it will still going to accommodate the nucleophile because it can attack the corresponding vacant d orbital. Okay. So, these are some of the example that if you have this two structure, now if you are trying to compare them for the substitution reaction rate, then you can see that corresponding silicon is 10 to the power 6 times more reactive compared to this one for corresponding carbon. What is happening here? You can see for this particular carbon, if you try to form a carbocation in the bridgehead position, that is difficult, and at the same time it is a tertiary. So, backside attack is also difficult. Okay. So, that is why SN1, SN2 is kind of unfavored here. But if you think about corresponding silicon, as I mentioned that silicon have no problem with that. Silicon go to not only can limit to the tetravalent, it can go to pentavalent, and from there it can able to then the silicon and the halogen bond going to get cleaved and then going to form the corresponding product. Another example here, I think this is about that if you try to go for SN1 solubilization rate for this compound versus you have a TMA. So, now here it is equatorial position, this is axial position. Now, when they are both in the axial position, now you can think about that carbon silicon. Okay. So, because this sigma bond can give electron density to the corresponding sigma star orbital here, and this donation is possible because they are in the anti-periplanar. That is why in this particular compound we will have a SN1 solubilization rate much higher compared to B or A, okay, because of this anti-periplanar geometry. So, other important thing I think I told you when I was talking about some of the enolate chemistry. I think if you remember, after the 1,4 addition, when we talk about 1,4 addition, I think that time I talk about these things that once you go for a 1,4 addition, you have this copper based nucleophile which is attacking here, and if you remember I talked there that once this will going to form this corresponding enolate, and now it has two different options. Starting from this, if you give this two different things, means if you take a carbon based electrophile or if you take a silicon based electrophile. Okay. So, if you have this SiMe3X versus if you have alkyl halide like methyl iodide, what will happen? Okay, it is saying that because of this the hard soft Lewis acid concept, I think that time also I mentioned that the silyl halides is a harder electrophile and the alkyl halides are a softer electrophile, and oxygen is a harder center compared to the carbon. Okay. So, that is why you see that once you have a silicon, then it is going to react with the oxygen. Once you have alkyl halide, it is going to react with the corresponding carbon and C alkylation going to happen. So, once you have this the silyl chloride, now you can able to form various compounds starting from that. Once you have this silyl chloride, now if you treat with the corresponding thiol, that can form the corresponding thiosilane. If you have the corresponding amine, you can have a silane amine if you treat with the alcohol, it is going to form the corresponding silyl ether, and if you go for a reduction, then it can replace this the silicon chlorine bond to put silicon hydrogen bond to form silane, silyl acetate if you treat with acetate, and if you have a treat with water, it is from the silanol, and it is a very important compound. I am going to come back in a minute, because from silanol, depending on the structure of the silanol, you will be able to make different type of polymeric compounds. So, that is going to discuss you to the compound called silicones. Okay. So, silicones or the polysilicones silicones are polysiloxanes, or the siloxanes is a polymer composed of repeated unit of siloxane. That means you have this silicon and oxygen. So, siloxanes are produced by the hydrolysis of the corresponding chlorosilane. So, starting from the chlorosilane, you are going to produce the siloxanes. Okay. Now, the question comes, depending on how many chloride you started with trimethyl silyl chloride, or you started with dimethyl silyl dichloride. So, depending on that, you will be able to make different polymers. So, from here, once you have a trimethyl silyl chloride, once you hydrolyze, you can form this trimethyl silanol, but it is not going to stay like that. It is going to form immediately going to form a dimer, forming this hexamethyl disiloxane. Okay. But the things happen once you have a dimethyl dichlorosilane. Okay. Then what is going to happen? Now, after the hydrolysis, you are going to end up forming this 2 chlorine will be replaced by 2 OH group. But once you have this compound, this is going to react with again with this compound and going to end up forming the silicone. Okay. Because this the product once is going to form, this oxygen can now attack to the silicon. Okay. And going to end up forming a straight chain polymer with active hydroxyl group present in the both side. And now, if you have a 3-chloride methyl trichlorosilane, you can end up making a complex cross-linked polymer, because you can understand now the polymer cannot be a straight chain. It can happen it can happen on both sides. Okay. That can end up forming a complex polymer. But if you have a 4-chloride like silicon tetrachloride, these are very strong Lewis acids. Okay. So, it will very exothermic reaction going to happen if you treat it with water, and immediately it is going to convert to the corresponding silicon oxide. And if you are in the lab using silicon tetrachloride every day for the performing different type of reaction, these are very good Lewis acid. We are going to explain that in other class. So, it is going to hydrolyze first and going to form a silicon dioxide. So, in this particular part, I talk about the discovery of the silicon, some of the important property of silicon, this alpha effect, beta effect. I talk about some of the in the formation of the carbon ion in the alpha position, and then the synthesis of the different type of silicon. Again, here are the references. Again, thank you so much for coming to the class, and I am going to see you guys in the next class. Thank you.